In this lesson, we'll discuss the mean value theorem. So for this theorem, we have to have a function that is assumed to be continuous on a closed interval and differentiable, meaning you can take the derivative, within that interval. So for this picture I've drawn here, this is my function y is equal to f of x. And I'm defining it starting here at what I'll call a, and going to here, which is b. And then the y value at a, well, that's f of a, and the y value at b is f of b. If you assume these things about this particular function, I'm going to geometrically describe what the mean value theorem says. I'm going to draw a line connecting f of a and f of b, these 2 points. So I'll draw that like this. The slope of this line, which I'll call m, is equal to f of b minus f of a all over b minus a. The observation that you can make is there are places on this function inside the interval from a to b where the slope of this line, a secant line, is equal to the slope of a tangent line. One place is about here. So I'll draw this spot on my graph. And this occurs at a value that I'll call c. If you draw the tangent line here, the slope of this tangent line, which is equal to f prime of c, is actually the same as the slope of this line. Now, this isn't the only place where this happens. It looks like there's another spot right about maybe here. So it looks like at this spot, the same thing happens. So maybe it's a C1 and a C2. But this is the conclusion of the mean value theorem. If you have a function that is continuous on a closed interval, and you can take the derivative with inside the interval, then the slope of the line between the endpoints is going to be equal to the slope of the tangent line somewhere within this interval, possibly at multiple places. So I'll describe that conclusion over here. So with those assumptions, we can say then there is a number, which I'll call c, in the interval from a to b, such that the derivative evaluated at c is equal to f of b minus f of a all over b minus a. And there is one, but there could be more than one depending on the function that you have. Let's apply this in a couple of examples. In example 1, does the function f of x equaling x cubed minus 3x plus 5 satisfy the hypotheses of the mean value theorem on this interval? And if it does, can we find all those numbers c inside that interval that satisfies the conclusion of the mean value theorem? Let's start with this first part. What does it mean to satisfy the hypotheses of the mean value theorem? The first one is the function is f of x, which of course equals x cubed minus 3x plus 5, is f of x continuous on the interval from -2 to +2? Is this true? And the answer, of course, is yes. And the reason is f is a polynomial. They are continuous everywhere, and therefore they're also continuous on any interval that you look at. The other hypothesis is f of x, again, equaling x cubed minus 3x plus 5, is f of x differentiable on the interval from -2 to +2, so not including the endpoints? The answer here is also yes. And that's because if you take the derivative, you get 3x squared minus 3. So yeah, it's differentiable because you can take the derivative, and the derivative exists on this entire interval. All the hypotheses have been satisfied. Therefore, is the conclusion true, which I'll put over here? Can we find all the numbers c in the interval from -2 to +2 such that the derivative evaluated at c is equal to, in this case, f of 2 minus f of -2, all divided by 2 minus -2. And let me just write this so it shows up a little better. The derivative of the function evaluated at this number is equal to the slope of the secant line between the two endpoints. Essentially what I'm going to do is I'm going to take c and put it into the derivative. I'll put that here. And I'm going to compute this number in my calculator. I'll set them equal to each other and try to solve this for c. So first, f prime of c, that is equal to 3c squared minus 3. Is that equal to, all right, f of 2 is 7, minus f of negative 2. F of negative 2 is 3. The denominator is really 2 plus 2, and this is equal to 4 over 4. So can you find number c where the derivative is equal to 4 over 4, which is also 1? So I'll solve that over here. This is ultimately what we're doing. When is 3c squared minus 3 equal to 1? Well, I'll add 3 to both sides. I'll divide both sides by 3. And I'll take the square root of both sides to solve for c. c is equal to plus or minus the square root of 4/3. And you can break that square root up between the numerator and the denominator, so you get 2 over root 3. And you can actually leave it just like this. You can also rationalize the denominator and write it as 2 root 3 over 3. Those are all fine. I think I'll record my answers like this. Okay, you want to take all of the answers that you get here, C, that fall within this interval. And actually, both of these do, both the positive and the negative solution. So you only want to include the numbers that are within this interval, so not equal to an endpoint even. So are the answers? The answers are C is equal to negative 2 over root 3 and also positive 2 over root 3. And geometrically, what this is on the interval of this function, you can draw a secant line between the endpoints. At these two numbers, the tangent line has the same slope as that secant line. All right, let's try this with a function that's not a polynomial, like, for example, the natural log of x. Same question, though. Does the natural log satisfy the hypotheses of the mean value theorem? Let's start with on the interval from -1 to 5. Will that be okay? So here we have the natural log of x. That's my function. And we're looking at it on this interval. And the answer is no. On this interval, the hypotheses of the mean value theorem are not satisfied. And why is that? The natural log of x is not continuous on the interval from -1 to 5. In fact, there's places where the natural log isn't even defined. You can try this yourself. If you put -1 into the natural log function, it's going to give you an error message in your calculator. This is only defined for positive numbers. So no, it does not satisfy the conditions on this interval. So no good. But what about this other one? What about if we look at the interval from 1 to 5? So that is f of x equals the natural log on this interval. All the conditions will be satisfied. First one, is it continuous? And yeah, this is always defined for positive numbers, and these are all positive. And furthermore, logarithms are continuous where they are defined. So I'm just going to say, yeah, okay, it's continuous. Is it differentiable? And this would be on the interval from 1 to 5, not including the endpoints. And the answer to this is, well, it's also yes. And the reason for that is if you take the derivative of the natural log, you get 1 over x. So you can definitely take its derivative. Is this always defined on this interval? Sure. The only number that would be a problem is 0, which is not in this interval. So continuous, yep. Differentiable, yes. Let's now find all of the numbers C that satisfy the conclusion of the mean value theorem. So what we're looking for is we want to find all numbers C in the interval from 1 to 5 such that f prime of C is equal to f of 5 minus f of 1 all over 5 minus 1. So I have a formula for the derivative. It's 1 over x. I'll call it 1 over c. By the way, you could actually just leave this 1 over x and solve for x, and that would be completely fine. I'm just going to continue using a c just because that's the letter that was used in the statement of the theorem itself. Well, anyway, so f of c, I think I'll put this over here. F prime of c is 1 over c. Okay, f of 5 is the natural log of 5. F of 1 is the natural log of 1. And we're dividing this by 5 minus 1, which is 4. The natural log of 1 is 0, meaning this whole thing just equals the natural log of 5 over 4. That's what we're looking for. All numbers C that satisfy this equation. The mean value theorem guarantees that when we find our solution, it will be inside of this interval. It'll be somewhere in here. How do you solve for C? Well, you can flip both sides of this equation. If you flip both fractions, you get C is equal to 4 over the natural log of 5. That number, if you check it in a calculator, it is greater than 1, but is also less than 5. This is the only number for which, if you look at the slope of the line on this curve between these points, the slope of the tangent line will be the same at this location here. In example 3, we're going to look at kind of a non-example of the mean value theorem. This says let f of x equal this function, x minus 3 to the power of negative 2. I want to find all numbers C within this interval such that basically the conclusion of the mean value theorem holds. Notice that this problem doesn't say anything about let's check to see if the function is continuous and differentiable on this interval. So let's actually just go ahead and try to find if this is true. Can we find all numbers C in this interval such that this happens? To do that, we will take the derivative of the function f of x. F prime of x is equal to negative 2 times x minus 3 to the negative 3. By the chain rule, we'd multiply by 1, which I'm not going to write. If I put c into this function, f prime of c, that's negative 2 times c minus 3 to the negative 3. Okay, what is f of 7 minus f of 1 all over 7 minus 1? Let's compute that next. So f of 7, let's see, that's equal to 7 minus 3 to the negative 2. That is 4 to the negative 2, which is 1 over 4 squared. The negative exponent becomes positive in the denominator, and that's a 16th. F of 1 is 1 minus 3 to the negative 2, which is negative 2 to the negative 2, which is 1 over negative 2 squared, and that's a 4th. So if we compute f of 7 minus f of 1 all over 7 minus 1, that's a 16th minus a 4th all over 6. I'm going to multiply the top and bottom by 16 to cancel all of the fractions within fractions. Okay, so if we distribute this to both fractions, we get 1 minus 16 over 4 is 4, divided by 6 times 16, if I multiply these two denominators together. That is negative 3 over 6 times 16. Let's see, 3 goes into 6 twice. 2 times 16 is 32. This whole thing is equal to negative 1 over 32. Okay, great. This is negative 1 over 32, which I'll set equal to this, and I'll solve it over here. So we have the following. Negative 2 times c minus 3 to the negative 3 is equal to negative 1 over 32. I think I'll divide both sides by negative 2. That gives me c minus 3 to the negative 2 is equal to, the negatives cancel, 2 goes into this denominator, 2 times 32 is a 64th. This side with the negative exponent, you could write with a positive exponent like this. And if you have two fractions equaling each other, you can flip both of them. So if I flip the fractions on both sides, I get c minus 3 squared is equal to 64. I'm noticing, of course, I made a mistake. These should all be 3's. I'm just going to go back and replace them. Sorry about that. Those should all be 3's. I bet you noticed that. Whoops. Okay, this was equal to this. I divided both sides by negative 2. I flipped both fractions. Now I don't have fractions anymore. To solve for c, I'm going to take the cube root of both sides. So if we take the cube root of the left and the cube root of the right. The cube and cube root will cancel. That's c minus 3. And the cube root of 64 is 4. And therefore, c is equal to 7. Fantastic. If this is true, we found every number for which it could be true, 7. But there's a problem. This number 7, is it actually within the interval from 1 to 7? The answer is no. So I'm going to just put over here, okay, c equaling 7 is not in the interval from 1 to 7. And the reason is, this parenthesis means we're not including 7. For the mean value theorem to be true, the number here has to fall within the interval. Like maybe it would be 6 or 5.2, but it can't be 7, and it can't be equal to 1. Because this did not work out, there's actually no number. There is no number c. So there is no c for which this is true. In retrospect, going back, why would that have happened with this particular function? The function f of x, the original function, could really be written as 1 over x minus 3 squared. This function is equivalent to this one. Is there any issues with this function being continuous or differentiable? And especially on this interval? And the answer is yeah. This is not continuous at 3. If you put 3 into this function, you're dividing by 0, and 3 falls within this interval. I'll just note that f is not continuous on the interval from 1 to 7. And the issue being x is 3 is the problem number. So if one of the conditions of the mean value theorem is not met, potentially this conclusion might not be true. I mean, it could work out. I mean, perhaps there would be a number c, but it turned out in this example, no, it did not work out. In example 4, let's suppose that f of 3 is equal to 1, and we also know that the derivative of the function is always 2 or more, and that happens when you're between the x values of 3 and 5. The question is how small can f of 5 be equal to? All right, to see what's going on with this problem, let's draw a picture. And what I'm going to do is try to graph the function f of x, or as much as I know about it since I'm not given an equation. We're told that at x is equal to 3, so 1, 2, 3 here, we're told that the y value is 1. So I know that about my function for sure. The other thing we're told is whatever this function is, if you're from 3 to 5, so from here to 3, 4, 5, if you're from here to here, the derivative of this function is 2 or more. And that just means if you draw the slope of a tangent line from here to here, the slope can never be less than 2. It can't be negative, it can't be 1, it must be 2 or more. I'm going to draw in a slope of 2 at this point, like this. So if you graph your function, it can never have a slope that goes lower than this line here. Now the question is, using this information, can you actually figure out, well, I don't know what the function is, there's like a lot of choices. What's the smallest y value that this function could equal at 5? So we're starting at 3 and we're ending at 5. The smallest would have to be here, whatever this is equal to. One way you can get this number nicely is by using the mean value theorem. So here's what I mean. We have our function f of x, but we have no formula for it. But what do we know about it? Because we're told this statement here on this interval, we know that f prime of x exists on the interval from 3 to 5. That is an assumption. And if a function is differentiable, meaning the derivative exists, then you know f is continuous on the interval from 3 to 5. So because we're told this is true here, we know it is continuous. And if it's differentiable on this interval, it's also differentiable inside the interval from 3 to 5 as well. What this all means is we can apply the mean value theorem to this problem, And what does the mean value theorem say? It says, by the mean value theorem, there is a number C in the interval from 3 to 5 such that f prime of C is equal to f of 5 minus f of 3 all over 5 minus 3. Okay, now we don't have a formula for the function, so we can't actually simplify this, but it turns out in this problem, that's a good thing. Here's why. Let's actually manipulate this equation a little bit, and I'll put that work over here. Okay, f prime of C is equal to, we don't know f of 5, but that's precisely the number that we're trying to answer something about. So I'll just write, okay, f of 5 minus, now we actually are told f of 3, it's equal to 1. So I'm going to put a 1 here. And I'm dividing by, okay, well, we have 5 minus 3. All right, well, that's 2. Let's take this equation and solve it for f of 5, meaning I'm going to multiply 2 to the other side and then add 1. And I think I'll write it like this. 2 times f prime of C is equal to f of 5 minus 1, and therefore 2 times f prime of C plus 1 is equal to f of 5. Or, if I reverse this, f of 5 is equal to 2 times f prime of C plus 1. Now the question is how small can this be? Well, this is equal to this. But we're told that this, the biggest it can be, or the smallest it can be, I mean, is 2. So that means this is always greater than or equal to 2 times 2 plus 1. If you replace this with 2, you're making this whole thing as small as it can possibly be, meaning this thing is always bigger than this. And this is a number. 2 times 2 is 4 plus 1 is 5. So what is the smallest f of 5 could be equal to? It's 5. It must always be bigger than or equal to this number. So that's our conclusion that we can draw here. F of 5, it must be bigger than or equal to 5. You could also reason that out by saying, oh, well, the slope of this line is 2, and it starts at 1. So if you go over 1, you go from 1 to 3. And if you go over 1 more, you go from 3 to 5. That is the smallest it could be. It could be bigger, but it definitely can be no smaller than this because we know something about the slopes of the tangent lines. So I answered the second part of this. Is it possible to determine how large f of 5 can be equal to? And the answer to that is no. Your function could look something like this, where you have a very large slope. And that means it can always be larger and larger and larger. So I can't put an upper bound on it, but I can for sure say, well, it can't be less than this number here. The other theorem that appears in this section is something called Rolle's theorem. And this is a special case of the mean value theorem. Let's describe it by using this graph down here. So the idea is going to be the same where I want to draw a function that is continuous on some interval and differentiable within inside that interval. So here's my function f of x here. So I'll label this as y is equal to f of x. Here's my starting point of a. Here's the ending point of b. So continuous function, differentiable inside this interval. But with Rolle's theorem, we're going to add in an extra condition. So we're assuming continuity, we're assuming differentiability, just like the mean value theorem, but we're further going to assume that f of a is equal to f of b. This was not assumed in the mean value theorem. What that means down here on your graph is that this y value is equal to this y value. So here is f of a, here is f of b, and we're assuming that they're the same number. So your y value where you start is going to be the same as where you end. What conclusion can we draw from the mean value theorem? So I'll write that here. The mean value theorem still applies. That means then there is a number C in the interval from a to b such that f prime of C is equal to f of b minus f of a all over b minus a. Still true. This is all just from the mean value theorem. But with this assumption, what can you say about this fraction? What is f of b minus f of a? Here's f of b, here's f of a. They're the same number. If you subtract them, you get 0. That is, I'll put over here, f of b minus f of a, that's equal to 0. And if you divide it by b minus a, still 0. So the actual conclusion we can draw with Rolle's theorem is f prime of c is 0. So really, we're concluding this here. This is still true, but you can reduce it to this. And geometrically, this makes sense too. F of b minus f of a over b minus a, which we know is 0, is the slope of the line between these 2 points, which I can put here in green. Here, that is the slope, which is 0. Are there places inside this interval where the slope of the tangent line is equal to the slope of this line? And the answer is yeah, there's a spot here. If you look at this spot, the slope of that tangent line is equal to 0, so I'll call that C1. And also here, the slope of that tangent line is also 0. So we know at least one exists, but there could be multiple ones as well. In example 5, let's show that the function f of x equals 3x squared minus 6x plus 4 satisfies the 3 hypotheses of Rolle's theorem on this interval. And once we know it does, we're going to find all numbers c inside this interval that satisfy the conclusion of Rolle's theorem. So for Rolle's theorem to be true, we have to ask, is f of x, which equals 3x squared minus 6x plus 4, is this function f of x continuous on the interval from -1 to 3? And the answer, of course, is yes. It's a polynomial. Polynomials are continuous everywhere. Is f of x, again, equaling 3x squared minus 6x plus 4, is this function differentiable on the interval from -1 to 3 inside that interval? Meaning, can you take the derivative and does it exist there? The answer is also yes. Again, if you take the derivative, we get 6x minus 6. This thing exists, and it's defined for all these numbers. The other condition that we need is f of -1, does that equal f of 3? I'm going to type this into my calculator and see if we get the same number for both. Well, it turns out that this is also true. We get that 13 is equal to 13. Okay, great. F of a equals f of b. We have a continuous function that is differentiable inside a given interval. We can now find all numbers c, and there must be at least one in this interval, such that f prime of c is equal to 0. So again, I want to find all c in the interval from -1 to 3, such that this happens. Here's my function f of x. I'll put c in place of x. That is 6c minus 6 is equal to 0. To solve for c, I can add 6 to both sides, and I can divide both sides by 6, and I get c is equal to 1. 1 definitely falls within this interval. This is the only number for which this is true, so we found that value. Let's look at an application of Rolle's theorem. In example 6, we're given this equation here, x cubed plus x minus 1 is 0. I want to use the intermediate value theorem to show that there is a solution to this equation, but then I'm going to use Rolle's theorem to show that there's exactly one solution, meaning there can't be a second one. Now, the first part of this question is something we did a while ago, using this theorem to show that there is a solution to this equation. Now, if you remember how that worked, the intermediate value theorem said that if you have a continuous function on a given interval and it goes from a negative number to a positive number, then there has to be a place inside that interval where it's equal to 0. So let's start there with the intermediate value theorem. My function f of x is equal to x cubed plus x minus 1. Can we find an x value where this is a negative number and then another x value where this is positive? Let's try to choose something obvious. So I'm noticing that if I put 0 into both x's, I'm left with -1. So starting there, f of 0 is equal to -1. So I just found an x value where my function is negative. I'd like to find a different x value where this thing is now positive. Again, maybe something obvious will work. It looks like the number 1 will work. If you put a 1 here and here, you get 2. 2 minus 1 is 1. So there's a number where this function is positive. So f of 1 is 1, which is a positive number. So on the interval 0, 1, f of x, which is continuous, goes from negative to positive. By the intermediate value theorem, there must be a place inside the interval where it equals 0. So I'll say there is, by the intermediate value theorem, there is a number c in the interval from 0 to 1 such that f of c is 0. This means we found a solution to this equation. We're going to use Rolle's theorem to show that there can't be a second one. To do this, let's suppose c and d are both solutions to x cubed plus x minus 1 is equal to 0. And we can assume that c is less than d. So here we're saying, okay, well, what if there were more than one solution? Not just c, but this other one, d. What would that mean? Since both of these numbers solve this equation, they're both equal to 0. So we have that f of c equals 0 is equal to f of d. We can use Rolle's theorem in this case because we have a continuous function that is differentiable on this interval and the endpoints are equal. So we can say there is a number, I'll have to call it something else, but I'll call it a. There is a number a in the interval from c to d such that f prime of a is equal to 0. Let's look at the derivative of f. F prime of x is equal to 3x squared plus 1. And we just found a number a where 3a squared plus 1 is equal to 0. If you try to solve this for a, you're not going to get a real solution. If you subtract 1, you get 3a squared is equal to -1. If you divide by 3, you get -1/3. And if you try to take the square root of a negative number, it doesn't work. It does not exist. So what this means is there can't be more than one solution. We know there is one solution, but the second you throw in a second solution, you arrive at this contradiction here, meaning it could never work in the first place. That's enough to say that, okay, there can be one solution, there can't be a second one, and therefore there is exactly one real solution to this equation on this interval. The intermediate value theorem found us one solution, and then we used Rolle's theorem to show that there could not be a second one.